Okay, so it's my pleasure to introduce you to the last talk of this session of Semiva regarding scalar geometry and the Calabi conjecture. Our last speaker is Benedetta Piroddi. She's going to talk about examples of Calabi-Yau manifolds. Please.
Thank you, Davide. And yeah, I mean, I think that since Lucas last session talked about hyperscalar manifolds, I had hyperscalar manifolds in the title, but then it dawned on me then there probably was no need to talk about hyperscalar manifolds again since he did. And also Zucchi talked about Calabi-Yau manifolds. So what I will do is just focus on some constructions of hyperscalar, professional definition of Calabi-Yau manifolds, and in particular, I want to focus on two ways to find the Calabi-Yau manifolds. One is how to find them basically in the wild. The other is how to construct them, starting from singular varieties and finding resolutions of them which are smooth and so can be Calabi-Yau. So just recall that. Let's just recall what the Calabi-Yau manifold is for those of you who were not focused enough in the last sessions. So a Calabi-Yau manifold is a compact. I will write MFLD to signify manifold every time. So Calabi-Yau manifold is a compact scalar manifold such that its holonomy group is SU of M, where M is the complex dimension. The complex dimension of our manifold. Okay. And yeah, so basically my talk will be divided into parts. The first is how to find Calabi-Yau manifolds as projective manifolds. Projective. Oh, the other way around. So projective manifolds with let's do it the other way around, otherwise some people who study categories will be mad at me. So projective manifolds with trivial first Chern class are Calabi-Yau manifolds. So we'll just give some example. And the important condition is this one. So for instance, we just take so 1A, we just take F, which is a homogeneous polynomial. And then we take the set of all points in the complex projective space such that F of T is 0. Okay, and this will be a hypersurface. It's a hypersurface. Homogeneous of some degree D is a hypersurface of degree D. Okay, and then we ask ourselves when is a hypersurface of degree D the Calabi-Yau manifold. And to do this, we have to verify this condition. And so what we do is something like this. We consider the line bundle L of x. L of x is the line bundle associated to x. And let me refresh your memory about how this line bundle is constructed. So basically, we take this line bundle here is defined as that line bundle such that there exists a section that goes from, in our case, CPM to our LX, such that x of little x is 0 if and only if little x belongs to little x. A section, a holomorphic section. Okay. Then, if we consider the class of the hypersurface X, and this lives naturally in the 2m-2 homology space of our variety. Okay, let's call this M again. And if we consider the Poincare dual of this, so this goes here, and basically this isomorphism here sends the class of X to the first shared class of the line bundle associated to our hypersurface. Now, what we use is the adjunction formula, because this is actually our C1 of X. And so we use adjunction. And the adjunction formula relates the canonical bundle of relates the canonical bundle of X to the canonical bundle of the ambient variety, so M, which is CPM, this way. This is the canonical bundle of X, and the Chern class is the Chern class of X is the Chern class of its canonical. So this is what we want to find. And now the canonical bundle for a projective space is just minus m minus 1 for a projective space of dimension m. Yep. Then since since the pickup of the projective space is generated by the hyperplane section, this is again a multiple of the hyperplane section, because it's this one. So this is again, if we consider the degree d here, this will be O of d. And so we find that A of x is trivial if and only if here we find we compute it here. So this is O of b minus m minus 1, and so if and only if b is equal to m plus 1. So what we found is that our hypersurface here has trivial first Chern class if and only if the relation between the dimension of the ambient space and the degree of our hypersurface is this one. Okay.
That definition should include also complex tori when you're building, right? Regarding the algebraic varieties.
I will come to that later.
Okay, perfect.
Yes. Yeah, I mean, not all Calabi-Yau manifolds are hypersurfaces.
No, but I was guessing that because in that.
Oh, yeah, for sure. Yeah, for sure. Here you also have a complex tori. Yeah.
But are they Calabi-Yau manifolds in this sense?
No, wait.
Because if they are flat, they.
No, you're right. If they're flat, they are not Calabi-Yau manifolds.
Yeah, they should have trivial polynomial, right?
Yeah.
So you have to take them with another metric, I guess, to. Okay, no worry. We can talk about it later. No worries.
No, but yeah, you're right. We don't want to consider. Complex tori are not Calabi-Yau manifolds. Yeah.
Okay.
If that's included in in this statement, like please add to the necessary condition to exclude them.
Okay.
Okay. So hypersurfaces only if the relation between the degree and the ambient space is that one. Then, okay. In a similar vein, we can consider also complete intersections of hypersurfaces. So 1B is complete intersections. So now we take Y, which is x1, xk, with these that are hypersurfaces of degrees d1, dk. And the important thing here is that they intersect transversally in Y. Intersecting. Okay. Then, if we have this condition, the dimension of Y is M, which is the dimension of the ambient space. M minus the number of hypersurfaces we're intersecating. And then, similarly to the case above, we just consider the differential formula, and we find that the canonical bundle of Y is trivial if and only if the sum of all the degrees of the hypersurfaces is n plus 1. Again, similar to that one. And of course, we also want that all the di are at least 2, otherwise you are just cutting with hyperplanes, which means that you're just going down from M to a lower dimension projective space. The other thing I wanted to say is that all the hypersurfaces of a given degree in a given dimension n space are diffeomorphic one to the other, which means that actually this leads only to one example for every choice of M, while this one leads to more choices, more non-diffeomorphic choices for every choice of M, but the number of choices is still finite. So we have a finite number, a single example with that one, a finite number of examples with this one. But yeah, not all Calabi-Yau manifolds are obtained like this. Otherwise, we would know, I guess, a lot more about them than we actually do. And the thing is that Calabi-Yau manifolds are actually easier to come by than hyperkähler manifolds, for instance, which means that this is doesn't exhaust them. And what I want to do for the second part is to give another way to construct them, and I will need a lot more machinery to do that. So let's erase some blackboards and go to part 2. Quanto tempo ho usato? Quanto tempo mi manca? Sì, no, assolutamente, ma ok, perfetto. Okay, so section 2 is devoted to crepant resolutions of Calabi-Yau orbifolds. And of course, I have to define all the stuff that is in this title. So 2A is, okay, what's an orbifold? Okay, so you can think of an orbifold as a manifold which is singular, but the singularities are all of the type locally, they are of this form, with the G that is a finite group acting holomorphically, which G is finite, and yeah, you're acting linearly. So in GI, finite, okay, already written. And so, for instance, the easier example you can think of is that you do exactly that. So you take a manifold M, complex manifold, and you take your group G that acts on M morphically, and then the quotient M over G is an orbifold. But not all orbifolds are obtained like this. So to give an example which is not obtained like this, you can think about weighted projective spaces, which I don't want to say too much about them. So this is one. Example 2 is weighted projective spaces. Which are, think of them as projective spaces in which some of the coordinates, and all the coordinates if you want, have a different weight to them. So instead of considering x0 to xm, where lambda x0 xm is equal to itself, which is normal projective space, here you put some higher power of it. So for instance, lambda of x squared sorry, the other way. Yeah, here you put like this, lambda square of x0, and then, for instance, lambda x1. So you just manipulate the relation here to include some weight, to assign some weight to some of the variables, which is different from the others. But again, yeah, I don't want to talk about them too much. They are useful. For instance, when you talk about, I don't know, when you talk about some manifolds, you want to describe them as double cover of another manifold, so they have an equation which looks like this. Then you want your T to have a different weight than the x0 and this, of course, all being in a projective space. So this is a homogeneous polynomial, this is square, so you have to arrange it. If you want to, yeah, if you want to describe this thing in a bigger projective space so that T becomes one of the coordinates, you want it to have, you want it to be in a weighted projective space which has weight 2 for T and weight 1 for the others. Yeah, okay, enough for the tangent. Let's go back to our orbifolds. And yeah, I want to give some technical details about them. For instance, now we have singularities on our X orbifolds. Again, X is always the object I'm referring to. So now let X be a complex orbifold. We say that it's scalar if it's a non-singular part, so X non-singular, you have a scalar metric on this. A scalar metric. Okay. And what happens near the singularities? You always have, let's take here a point, then there exists a neighborhood U of little x, such that U is of the form C m over G, and G near here, near x, can be written like this, where H is G invariant. So basically, it's a scalar metric over the non-singular part, and then on the singular part, it becomes a quotient of another scalar metric on the covering CM of that neighborhood of your point. And actually, this is a kind of general principle that you use to study orbifolds, in the sense that you kind of translate whatever is your question on your orbifold, you translate it to a G-invariant question on some cover of your orbifold, which can be only a local cover, so then you have to patch things together, or in the case you have obtained your orbifold like this, you translate it to a G-invariant problem on your manifold M. So with this like way of thinking in mind, you can, for instance, take again M. M, you take it as a Kähler manifold, and so this has a Kähler metric G, but G is maybe not G invariant by itself, but then what you do is that you can take G prime, which is basically the medium of the images for every alpha and G of your first look, and then this is G invariant. And this way, the quotient term over G is scalar. So it basically amounts to choose a G invariant metric, but you can always do that on the top manifold, but you can always do that just taking this kind of average. Okay, and with this way, you can also define what is the first check class of your X in general. So again, don't think about the quotient of a Kähler manifold, but think about the actual definition in which locally you have singularities which are of this form. So to define the first check class of X, you do it like this. So if for every little x, which is in the singular points of X, the stabilizer of little x is if this is a special linear subgroup. So if G is acting with determinant 1, then what happens is that this doesn't have any problem. So since here you're acting with determinant 1, the quotient. Okay, so basically the canonical bundle will be defined normally as a line bundle over the singular points. So this is a like two-line bundle on X, and you don't have any problem. So this is a two-element a class in cohomology. Otherwise, basically what happens is that instead of having a line bundle on X, you have a line bundle which on the singular points which you don't have these conditions. So the fiber over little x is of the form this point here. So it's not a line bundle anymore over that point. But for what amounts to the constraint class, doesn't change much in the sense that now this becomes well defined with rational coefficients. And this is not a problem because for the purposes of the Ricci forms, you need coefficients in R, so everything is fine, yes. And with this, you can basically restate the Calabi conjecture for orbifolds. And what you find is this. So you just restate it as when you have X, which is a complex with C1 0 and admitting Feynman matrix. Then there exists a unique Ricci flat matrix for every matrix of X. And you can also define the holonomy group of your orbifold. And with that, you can define what a Calabi-Yau orbifold is. So that we get to the thing that we needed here. So you define the holonomy of the Kähler metric on X as just the holonomy of what you have on the smooth on the non-singular locus. So G tilde, where G tilde is defined from the non-singular locus. So basically, what I used, I defined it at some point. Maybe I deleted it. Yeah, I think so. So you just use the one which is defined on the non-singular locus, and which, when you look at it near a singular point, becomes a G-invariant metric on the covering open disk. Okay, and with this, you define a Calabi-Yau orbifold as one such that the holonomy is SU. Now, a remark that I found interesting. Oh, I think I didn't say it, but the reference for all of this is Joyce's book. So I found this remark, which I think is kind of interesting, which is that since for every little x, which is singular, in the singular locus of x, the stabilizer group, of course, since the holonomy is SU of M, this is contained in SU of M, but SU of M is contained in a special linear group. Then what you have is that the codimension of the singular locus in X is greater or equal than 2. And this is because if you think of all the elements which are of all the elements of G, and you express them as matrices acting on some neighborhood of your points, then because of these conditions, you want it to have determinant 1. But if the codimension is 1, that means the codimension of the singular locus is 1. This means that you are fixing all the coordinates near your singular point apart from one coordinate, which is sent to some root of unity multiple. And if you do this, the determinant of this matrix will never be 1. So this is not in SLO in the special linear group. And so basically you cannot have this situation, which gives you this condition on the singularities that the Keller orbifold cannot meet. Yeah, so for Keller orbifolds, sorry, for Calabi-Yau orbifolds. Because of this, basically. And this is not in general true for complex orbifolds. If you add the Calabi-Yau conditions, it becomes true. And like coming back to our quotient manifolds. So now we are back to M, which is now a Calabi-Yau manifold, and G, which acts on M monomorphically. Then the quotient M over G will be a Calabi-Yau orbifold if and only if the volume form on M is a G invariant again. So all of this is quite rational to expect. And the thing is that you cannot do the trick I did before for Keller manifolds, where you started with whatever metric you had, and to get a G invariant metric, you just had to multiply it just to take an average. You cannot do the same for your theta, because theta is unique on M. So you cannot just scale it, just change it for something else. And so this condition here is a true condition, is not something you can escape. Yeah. And now I think we are set with Calabi-Yau orbifolds. We need to talk about crepant resolutions. Okay, now a crepant resolution is something like this. So you have your X here, and you get X tilde, which is a normal and non-singular variety, and pi, which is a proper map. And I think I need the proper, okay, sorry, a proper birational morphism. And crepant means that the canonical of X tilde is the fullback over T of the canonical of X. And it's crepant because in general, because it's not discrepant. So because when you pull back, the canonical bundle of X tilde is not different than the one on X in some sense. It's just a pushback of it. And the crepant resolutions are not such an easy thing to find. In general, when you're talking about isolated singularities, you just you can resolve them locally. If you're thinking, if you have singularities which are not isolated, it becomes a lot more difficult. What I will say about this is that the singularities of this form, this admits, in general, a crepant resolution. If it admits a crepant resolution, this is G needs to act as a special linear group. It has to be contained in a special linear group. And for Calabi-Yau orbifolds, this is not a condition, it's a trivial condition. For other orbifolds, it's not trivial. And when m is equal to 2, they always exist. So crepant resolutions always exist. And they are known as ADA, because of singularities in codimension singularities on surfaces are always admitted crepant resolution. They are known as ADA singularities. They have a whole theory about them. Not only exist and uniquely. Always exist, of course, uniquely depending on G. For every G. This is also. This is not worded in a way that is comprehensible. Crepant resolution always exists uniquely. Yeah, unique depending on G. So for every G, only one. Okay. And the other thing which is interesting. So for m equal 2, they exist and they are unique. For m equal 3, again, it can be proved that given this condition, so X is a complex orbifold, such that for every little x, which is singular, its stabilizer group is in SL over MC, which again is a condition I have to ask. If I don't ask Calabi-Yau, then there exists not necessarily unique a crepant resolution. And we can actually prove it in some sense. I don't want to give all the details. But basically, when you're working in dimension 3, you have this. You have your singularities can be of two forms. So basically, you either have a singularity which is the product of a line and a singularity in dimension 2, or you have an isolated singularity. Or isolated. And for these ones, you use this type of equation here. And then for the isolated singularities, you just resolve them locally, basically introducing a P2 fiber over your point, just blowing up. And since you don't have conditions for the gluing, because these are isolated, and over here you can always resolve them as surface singularities, you can always patch them together. To a global. So you can always actually resolve complex orbifolds of dimension 3. Complex dimension 3 again. And with this, I want to talk about how you actually get Calabi-Yau orbifolds with this. So basically, when you start with the Calabi-Yau orbifold, you have that it's trivial. That it's first class is trivial. And when you take a crepant resolution, because of the crepant condition, also the first class of the Grover manifold will be trivial. The only thing is that to get the Calabi-Yau manifold, you don't want it to disconnect. You don't want it to lose the simply connectedness. And for this, you usually need more conditions. The other thing is that if this is scalar and you take a crepant resolution, in general, you cannot expect this to be scalar, but there always exists a crepant scalar resolution. So maybe it's not the one you took, but one exists. And because of this, you kind of have to be careful. So it's not that every time you take a Calabi-Yau orbifold and you take a crepant resolution, it becomes a Calabi-Yau manifold. There can be more conditions than that in general. But I want to close with an example where everything looks good. So let's call it 2C. And our example will be the resolution, the resolution of the quotient of complex solid. Okay. And I start with T6, so a torus of real dimension 6 of complex dimension 3. And this is obtained by taking C3 and taking the quotient by a lattice. And this lambda here is the third root of unity lattice. So if your Z is E, then you take all the points of the form A1 plus Z1, E2 plus Z2, A3, let's say B3, where all the AI and the DI are in Z, so integer. This is a lattice lambda, and this becomes a torus, complex torus. And then you take an automorphism. Let's call M our torus. And then you take an automorphism that sends a point on your torus to Z. This is, of course, an automorphism of M. And yeah, it's holomorphic. Yeah, sorry, of course, you're working on the torus, so you can think of it actually as lateral classes for the quotient. So, yeah, just add the cell. It's an automorphism, and of course, it has order 3 because this is a third root of unity. And M of the group generated by alpha is singular in 27 points. Basically, because you can think of your torus, you can think of it basically as the product of 3 elliptic curves. This doesn't always happen, but you can default to it. And the triple points on an elliptic curve are 9. So you take 9 to the power of 3 becomes 27. So this quotient is singular in 27 points. And locally, around the singularities, you get neighborhoods which are of the form C3 over the group of order 3. And here again, you can resolve these singularities by blowing up each of these points, because they are always related. 27. So you get a CP2 in place of each of these singular points. And what you get is actually a Calabi-Yau manifold. And I think I will stop here.
Okay, thank you, Benny. Are there any questions or remarks? Even from our audience at home? I have one very quick, but you mentioned that this is a necessary condition, always. And if I get it correctly, it is sufficient if m is equal to 3, right?
Yes.
But are there characterizations for higher dimensional cases of this fact? Outside the Calabi-Yau example.
I don't think there are, because as far as I know, in general, crepant resolutions are constructed like on examples, on concrete examples. Like you cannot, like you can. There are some general things. So, for instance, in higher dimension, you use small resolutions, but to construct a small resolution, you have to think of it. Like there is not a general recipe to construct them. So I think it's actually a very difficult thing because, as far as I know, there is a whole subject which is minimal model program, which is which aspires to like find minimal models for varieties, basically taking partial crepant resolutions, which tells me that it's not in general a thing that you can do, and it's not unique in general. So yeah, I think it's
very open problem.
Yeah, I think that there is no general way to construct it, but it's also like a very sensible question.
Okay, if there are no more comments or questions, let's thank Danny again. Thank you again for joining us for this session of Semiva. See you very soon, I guess. And thank you to Fede as well for the whole organization section of this event. So thanks, Fede.